Hi, so today I'm going to be teaching you about integration by parts. By now you should be pretty comfortable understanding what an integral is and how to solve it for simple functions such as cos x or x, but you may run into trouble when you have multiple functions inside a single integral. And I'm going to teach you how to solve any combination of there. So when you have something like the integral of cos x plus x dx, to solve that you simply just split it up into the two separate functions. So you have the integral of cos x dx plus the integral of x dx. And the same is true for when you have the cos x minus x. You just split it up, and instead of the plus, it's a minus. Now, what might you do when you're multiplying or dividing them together? Well, if you follow the same pattern, you get the integral of cos x dx times the integral of x dx. But this isn't true. And I'm going to show you that later. But there are two ways to integrate this function above, this integral above. You could either use integration by parts or the tabular method. And next I'm going to show you integration by parts. So integration by parts can be shown with the equation the integral of u dv equals uv minus the integral of v du. But how do we figure this out? Well, first off, u and v are differential functions of x, and we find the equation above through the product rule for differentiation. So if we remember that the derivative of uv equals u times the derivative of v plus v times the derivative of u, which is the product rule, if you don't remember that, then we can figure out the above equation by taking the integral of the product rule equation shown. And that simplified will equal uv equals the integral of u dv plus the integral of v du, and simplified into the equation below. Now that you have this equation, you can use u, v, du, and dv as placeholders for the different parts of the integral that we had at the beginning of the problem. So if you set the integral of x times cos x dx to a part of the integral found with the integral of u dv equals uv minus the integral of v du, you can see that it's pretty similar to the integral of u dv, whereas x equals u and cos x dx equals dv. So now that you have these values, you want to find the other values in the u and v equation found earlier. So with u equal to x, and you take the derivative of that, du equals dx. And with dv equal cos x dx, you take the integral of that, and that equals v equals sine x. So now remember the equation that we found before, and now that you have all the values, you can just plug them in. So we find that the integral of x cos x dx equals x sine x minus the integral of sine x dx, which is equal to x sine x plus cos x plus c. It's true that there are often multiple options to replace each variable. In this case there are 4, as x could equal dv, cos x could equal u, or another combination using a different part of the equation that we found. But often you'll be able to see which is the most obvious place to put the variables in. And now that we know what exactly the integral of x cos x dx equals, we can prove that what we found before, following the pattern with cos x minus or plus x dx, doesn't actually work. So if cos x times x dx equaled the integral of cos x dx times the integral of x dx, it would equal sine x plus c times half x squared plus c, which does not equal what we found before. So this may or may not be simple for you. I'm sure with a lot of practice it will become more simple, but there are actually more complex integrals to solve that would take a lot more time if we use the integration by parts method. So if we have an integral like the integral of x to the fifth sine x dx, we don't want to use integration by parts because we'd have to integrate 5 times, do 5 times the amount of work that we just did to find the actual integral. So for that we use the tabular method. Now instead of integrating like we did with the integration by parts method, we can place the different parts of this integral into a table, like so, with one side x to the fifth and the other side sine x. Then we choose one side to differentiate and one side to integrate. We figure this out by knowing that one side has to go to 0. So if we have to choose one side to differentiate enough so that it'll reach 0 eventually. Sorry. So if we differentiate sine x enough, it'll never reach 0. It'll keep going in a loop with cos x and negative cos x and negative sine x and so on. But if we differentiate x to the fifth, eventually it will reach 0. So we differentiate the x to the fifth side, and then we integrate the sine x side the same amount of times. From here, now we're going to combine the two sides, and I'll show you how, and that'll get us the integral. So first off, we make sure that the differentiated side is in the right, is alternating positively and negatively, starting with x to the fifth being positive. And from there, now we just multiply diagonally, as shown. And then we add everything that's been multiplied together. And that'll get us our answer. So try and follow along, and I'll explain later for those that are confused. So we see here x to the fifth is multiplied by negative cos x. So it's negative x to the fifth cos x. And it's added to negative 5x to the fourth times negative sine x. And so on, plus c, of course. And this is the solution to the integral. So just imagine trying to use this integral in the integration by parts method and how long it would take to get that. Now we're going to do one more problem in both methods just to show you the differences between them and to go over the different parts so that any issues you have with one or the other or both are rectified. And I'll explain to you why I think the tabular method is a better method. So say you have the integral of x squared ex times dx. For the tabular method, you obviously split it into the two tables, and you differentiate the one side, the x squared side, because that'll get to 0 pretty quickly, and you integrate the e to the x side. Now, if you remember, you alternate the positives and negatives of the x squared side, you multiply diagonally, and you add together, and your answer is x squared e to the x minus 2x e to the x plus 2e to the x plus c. That was really quick. Now, for the integration by parts method, remember your formula, the integral of u dv equals uv minus the integral of v du. If you set u equal to x squared and dv to ex dx, then you can differentiate u and get 2x dx and integrate dv and get e to the x. If you plug that back in, you find that the integral of x squared ex dx equals x squared ex. Sorry, that should be minus the integral of ex 2x dx. But that integral is also not solved. So we need to do the same for that, and set u equal to ex and dv to 2x dx. Sorry, u to x, because we can factor out the 2, or just take out the 2, and dv to ex dx. So if we solve that more, we get the integral that we had found, the integral of ex 2x dx, that equals ex times x minus e to the x plus c. If we put that back into the equation, we get x squared e to the x minus 2x e to the x plus 2e to the x plus c, which is what we got before, so it's equal. So obviously the tabular method is a lot easier to use in most cases, as it took maybe 30 seconds to do this, whereas it took a minute or so to do the integration by parts. For me personally, it's a lot easier to do the tabular method. One, because I don't have to memorize the u-dv equation. Memorization is never your friend, and if you can stay away from that as much as possible, you'll find math becomes a lot easier. The tabular method is different from most other things that you'll do in calculus, but it's a lot simpler, and once you really get it down, then you can find there's really no integration by parts problem that is too hard to solve. But above all, remember that you should be fluent in both methods for the best results, and sometimes integration by parts is an easier method. I hope you enjoyed the video and learned a lot, and thanks for watching.